Chapter 9, Introduction to the T-Statistic, Part 1. The learning objectives or outcomes for this particular chapter include, first, we'll know when to use the T-statistic instead of the Z-score hypothesis test. Again, Chapter 8 entailed the four-step process we engaged in to perform a Z-score hypothesis test. We'll see in this chapter how the T-statistic is different and also learn when to use the T-statistic opposed to the Z. So there are instances where it's more appropriate to calculate T-statistic instead of a Z-score. We'll also perform a hypothesis test using the T-statistic. Luckily, we'll be using the same four-step process that we learned in Chapter 8. So in a previous video, I said that if you mastered Chapter 8, the subsequent chapters of 9, 10, and 11 would be quite straightforward because we'll be using the same procedure but calculating a slightly different statistic. And then finally, we'll evaluate the effect size of our treatment by computing Cohen's d, which we learned about in the previous chapter, and then the new statistic of R squared, which represent percentage of variance accounted for the treatment or difference between quasi-independent variable groups, and finally we'll learn how to compute a confidence interval. Tools you will need. We'll need to review how to calculate sample standard deviation from Chapter 4. So to calculate standard deviation of a sample, we learned that we first must calculate our SS, the sum of squared deviations. So just a review, we can calculate SS using what we refer to as the definitional formula, which was simply taking the sum of all our mean deviations and squaring them. Or we can use the computational formula, which is SS is equal to the sum of x squared minus the sum of x squared over n. And then once we calculate the sum of squared deviations, that enables us to calculate variance. And variance is equal to the sum of squared deviations over n minus 1, or SS over degrees of freedom. So those are equivalent to one another. So again, they only differ at the SS level in terms of the definitional versus the computational formula. Once we calculate our variance, that enables us to calculate our standard deviation, which is simply the square root of variance. But you also may see the following equations in the text. So we could say the square root of SS over DF, which is also the same as saying the square root of SS over n minus 1. So all of those three are equivalent to one another because what's in the square root is what we use to calculate variance. And so again, standard deviation is simply the square root of our variance. So we will be utilizing these equations quite a bit from this point forward. And the reason is the difference between a t-statistic and a z-score is the fact that we don't have the population parameters, specifically population variance, to calculate our standard error. So we're going to use our sample statistics to estimate what those population parameters are equal to. The next tool that will be useful in this chapter is standard error. And we learned that standard error of the mean is equal to the standard deviation of the population over the square root of n. And that's equivalent to saying the square root of our population variance over n. So again, you'll see both of these equations. And in fact, the second equation will be equated to the sample or estimated standard error of the mean that we're going to discuss and learn about in this chapter. So get used to this second equation because that's the format that will be utilized more readily in chapters 9, 10, and 11, and I'll explain more in a little bit here. So again, the standard error of the mean is simply expressing the average difference. So again, it's the average difference, or we can say expected difference, between the sample statistic, the sample mean, and the population mean. So it's what we expect would be a reasonable difference, because again, when we take samples from populations, we expect them to be similar to the population but not identical. So the standard error represents, on average, what would we expect this value to differ from the population. So it gives us a numeric value, an average difference. And then finally, we'll need to recall the hypothesis testing steps 1 through 4 that we learned in Chapter 8. And to review, those steps include step 1, we state the hypothesis, which includes indicating what the null and research hypotheses are, and also includes the proper notation given whether we're testing a two-tailed or one-tailed hypothesis. Step 2, we set the criteria for decision. We'll be doing the same with the t-test in this chapter. And then step 3, we collect the data and compute the sample statistics. Step 4, we draw our conclusions or make our decision. So again, we'll be utilizing that 4-step process or procedure to conduct a t-test in this chapter. Before the t-test is presented, it's a good idea to review what we learned in Chapter 8, which is the application of a z-test. So in Chapter 8, we presented the statistical procedures that allow researchers to use a sample mean to test the hypothesis about an unknown population mean. These procedures are based on a few basic concepts. First, the sample mean, m, estimates and approximates the population mean, mu. Next, the standard error describes how much difference is reasonable to expect between the sample mean and the population mean. And again, the computation to calculate that is seen here. So standard error is equal to this population standard deviation. So population standard deviation over the square root of n, or the alternate equation is the standard error is equal to the square root of our population variance over n. Again, those are equivalent to one another. And as I mentioned previously, when we say the expected or reasonable amount between sample mean and the population mean, that's the same as saying the average difference. So whenever you see the word standard, you can replace it with the word average. So we've computed an average difference that still constitutes something similar to the population mean but slightly different. And we're going to use these calculations as a basis to learn the new calculations for the t-statistic. Finally, to quantify our inferences about the population, we compare the obtained sample mean, m, with a hypothesized population mean, mu, by computing the z-score, and we do so using this equation. So z is equal to m minus mu divided by standard error, and which is also the standard difference or distance between m and mu. So it's often a good time, or good idea, I should say, to take an equation and verbally express it. What does the numerator represent? What does the denominator represent? So here again we're saying that this, which we have been referring to as the mean difference, can be expressed as the obtained difference between the data, right? We're going to collect data which produces our sample mean, and hypothesis, which is representative of the untreated population mu. And again, that's one way of expressing it, expressing the numerator. Another is simply to say the mean difference. And the denominator represents the average difference or expected difference or standard difference or distance between the sample mean and the population mean. And again, the whole goal of computing the z values is simply to standardize our sample value to see if it resides in what we learned about in Chapter 8, which we refer to as the critical region. If our sample mean is somewhere close to the population mean, then that leads us to fail to reject the null, that we accept the idea that there is no difference between the sample statistic and the population parameter. However, if our sample mean falls out in one of the tails, either of the tails, again, if we're applying a two-tailed test, then we are able to reject the null. Again, we're rejecting the idea that there is no treatment effect and providing support that there is. And we're doing so because the difference between these values is large enough and statistically speaking large enough for us to reject this idea that nothing happened. And we have support to say that something did happen, that the treatment did have an effect. Again, the goal of the hypothesis test is to determine whether the obtained difference between the data and the hypothesis is significantly greater than would be expected by chance. Again, if we see a difference, our job as researchers is to determine, is that difference due to treatment or is it due to chance? And the further out that sample statistic is out into the tails, the greater likelihood that it's not due to chance and it's due to or as a result of treatment. So when the z-scores form a normal distribution, we're able to use the unit normal table, Appendix B, to find the critical region for the hypothesis test. And we learned how to do that given alpha at 5%, two-tailed test, alpha at 1%, using a one-tailed test, so on and so forth. But again, this is all contingent upon having a normal distribution of sample means. And the only way we can generate a normal distribution of sample means is when we adhere to one of these two criteria. First, our sample size must be greater than 30, or if the original distribution is approximately normal. So if the original distribution is normal, n can be any size. If the original distribution is not normal, then as long as the sample size that we're using to generate a distribution of sample means, as long as it's greater than or equal to 30, then we are able to utilize the unit normal table to talk about probability of these values occurring. So again, the goal is simply to determine if the sample mean is significantly different from the hypothesized population mean, and which will allow us to draw conclusions regarding the null. Are we going to reject the null, or are we going to fail to reject the null? Sample means in the critical region enable us to reject the null. Sample means in this area, in the center area, mean that we fail to reject the null. And incidentally, if we do have values falling in that blue region, let's just say, for example, our untreated population mean was equal to 100, our sample mean was equal to, let's say, 105, and our critical region was set, and let's just say, for instance, it fell here in this region, and we then conclude that we failed to reject the null. Technically speaking, what we're saying is that 100 is equal to 105. And you may say that doesn't make any sense. Numerically speaking, we know that they're not equal. But statistically speaking, that value of 105 wasn't far enough from 100 for us to say that it's different. And that the difference that we're seeing between 100 and 105 is as a result of sampling error, right? We talked about sampling error way back in Chapter 1. Sampling error is the natural discrepancy between a sample mean and a population mean. So the only reason we would see a difference if we selected a sample and administered treatment and generated a value that was pretty similar to the untreated population mean, that difference isn't due to treatment. It's simply due to chance, sampling error. So hopefully you're thinking in those terms as, what are we doing and why are we drawing these conclusions? Again, it's all about, is that value different enough for us to support this idea that the treatment is the reason why the value is different, opposed to it's just by chance that we selected the sample that generated a sample mean different from the untreated population mean. Now that we've reviewed how to engage in a test, and we've kind of gone over the basics. Hopefully we've mastered that from Chapter 8. We're going to discuss some of the flaws or shortcomings of the z-score hypothesis. So the problems with the z-score are as follows. The z-score requires more information than researchers typically have available. So again, remember that we would need mu and standard deviation because we're calculating the mean difference between m and mu, and we're calculating standard error. Again, standard error of the mean is equal to standard deviation of the population over the square root of n. And we've discussed since Chapter 1 how difficult it is sometimes to have access to the population. And in fact, the reason why we engage in inferential statistics, by definition, inferential statistics means that we're taking sample data to draw conclusions about populations. And one of the reasons we do that is because the lack of access and information we have about a population. So the z-score requires that you have population parameters, both the population mean and the population standard deviation, which is not always the case. In fact, most often we won't have those values. So if we don't have population mean or the standard deviation of the population, then we're prohibited from engaging in a z-score test or a z-test for a hypothesis procedure. However, there are some instances where we have that data. There may be data that is readily accessible, such as IQ scores, standardized test scores for students in public schools. So there are some populations where we have this information available, but in most cases we don't have that. So again, this z-test or the z-statistic requires knowledge of the population standard deviation, or we would need at minimum the variance, which again is unlikely to be accessible for most populations. And then finally, researchers usually have only the sample data available. But that's, not a bad thing. That's actually a good thing, that we recognize that samples are coming from the population. And if they're randomly selected, then most likely they will be representative of the population. So our solution to these problems is simply to rely on a sample or sample statistics as estimations of the population parameters. But again, it's important to first review the procedure of engaging in a z-test, and then at this point recognize some of the flaws or the problems that we may face if we try to conduct a z-test. Again, the z-test compares a sample to a population when population parameters are known. So again, back at the beginning of this lecture, I introduced one of the learning objectives, which is to determine when it's appropriate to use a t-test or t-statistic opposed to a z-statistic. And this is the reason why. We would opt to use a t-statistic instead of a z-statistic when we don't have all the population parameters, specifically the population standard deviation or variance. So if we don't have that information, then the z-test is not possible, but we can use the alternative t-test, which is engaged in the same process of comparing a sample mean to a population mean. So that concludes this brief introduction to Chapter 9, and all we've done to this point is review essentially all that we did in Chapter 8, and specifying the components of a z-test, and then understanding its limitations in the sense that we need a lot of information to engage in a z-test. And in the next video, I'm going to introduce the t-statistic or t-test as an alternative to the statistic or conducting a hypothesis using a z-score.